Thank you all for coming. I don't know if anybody was aware, but last night we did experience an earthquake here in Tampere. As I was walking home from dinner, the road was just shaking back and forth. I don't know if anyone else had that same experience, but it had to be an earthquake, Tampere. So, 275 million years ago, the supercontinent rock band Pangaea. Everyone heard about Pangaea? So the super rock band Pangaea was formed. 200 million years ago, the lead singer and the bassist got into an argument, and so they started to break apart. 150 million years ago, China, who was the lead singer, left for a solo project with Asia, and North America and Europe just started to separate. They want to go their own separate ways. 130 million years ago, it was really over. North America completely separated from Europe. Pangaea was a thing of the past. And 50 million years ago, Australia moved away from Antarctica, citing a frigid relationship. They never knew if they were going to get back together. Pangaea had just completely separated. Modern day, compared to 50 million years ago, in 1912, German scientist Alfred Wegener proposes a theory of continental drift, where he proposes that these continents that were once Pangaea were wandering around the globe. He called that continental displacement, which was not to be confused with his continental drift theory called incontinence. You can use that one, thanks. Japanese seismologist Kaiyu Wadati in 1936 proves the theory is real of underground deep earthquakes as Godzilla is released in Tokyo and wreaks havoc. 1965, we're into now British geologist Sir Edward Ballard, who has a theory that he thinks that these superficially separated members of Pangaea are actually still secretly connected at their continental shelves, so that the continents are still connected there. Almost now really present day. 2016, Kent Condi makes a statement. I think he's in New Mexico. I forgot where he was out of. But he makes a statement that tectonic plate movement has increased, nearly doubled over the last 2 billion years. I don't know who could argue with that, but so I propose in 2019, for all of you that have these balls, that we do our best to squeeze all the continents back together so we can stop earthquakes from wreaking havoc on our buildings. My presentation overview is about earthquakes and seismic events and how they affect buildings. In fact, not how they affect buildings, but how we then took glass cladding that is usually installed within buildings and tried to make a mounting system that was more friendly to withstanding the shaking back and forth of earthquakes. So when you are mounting glass in a building, whether it's way up high on a wall, whether it's overhead, whether it's a facade, whether it's right behind a reception desk or whatever, we want to make sure these things are sound physically and go through testing. This presentation will discuss our system that we then took to seismic testing to see if it would be compliant with AMAA, American Architectural Manufacturers Association standard test, which is 501.6 in the US, which tests a system for its ability to withstand shaking back and forth. And we'll show some pictures and graphs. The third-party testing was done by Intertek out in Fresno, California. So seismic events. In the US alone, 4.3 million businesses are impacted by seismic events. The amounts of costs involved are huge. And if I remember correctly, there it is, $2 billion per year. This is, again, in the US alone, of effects of seismic events on buildings. The earthquakes are very unlikely to happen, so it's called a low likelihood event, but there's a high risk. If it does happen, there's a high cost involved within the buildings. Again, last night I was talking about just, the Earth doing this. It has been shown that as little as 0.02 Gs of force, which is, 2% of gravity, can cause you to fall over if it's coming at you on the, sideways. So that's just what a little bit of shaking does. Some of these earthquakes get as high as 3 Gs of force, 3 times gravitational movement back and forth. Typically, the real strong ones are just over 1. But this chart kind of shows the severity and what it does, that the weak ones to the light ones of very low G-force, there's really no destruction, although you get wobbly and things fall, but there's usually no damage, all the way up to the ones that are above 1.25 of G-force, of the force of gravity being very heavy damage and extreme conditions. So stronger forces can cause things to fall off walls. The non-structural parts of the building, although they're part of the building, they're not the main structure, they're attached to the main structure, they can cause 65 to 85% of the cost of the building in damage, even though they're not part of the structure. They're attached to the moving parts. So on this slide, the main thing is that the parts of the building that aren't the building itself, but the building and the non-structural parts are the most likely cause of injury or death. And so we were tasked with figuring out a way to make our glass and the way it's mounted to walls less dangerous in case of earthquakes. We had been putting glass in all over the US and other parts of the world, and typically being asked to mount it now, more recently than before, and what kind of mounting system we have. As we got into the mounting portion of working with our glass, we started getting asked, well, how does that hold up seismically? And although facades, other building materials had been tested a lot for seismic capabilities, there hadn't been much testing for wall cladding systems, for just decorative glass. A lot of people hear decorative glass and they just think, oh, it's that pretty stuff. It doesn't have any structural necessity. It doesn't have any safety. And thank you. Adam over here was, he led me into a discussion earlier this week where I told him we did decorative glass. And then we started talking about safety standards. And he's like, well, why are you talking about that? It's just decorative. And I'm like, what do you mean? It's like, well, most people talk about decorative. They're just talking about pretty stuff. And I all of a sudden thought about that, is that we've been making safety glass, tempered glass, laminated glass to meet all the standards. And so I appreciate that comment and feedback, that decorative can also be safe, and it also can be seismically safe. So people on the West Coast in California had been really active in wanting to have seismically sound materials as well as mounting systems to put in. We have just completed a job out in California in San Francisco where the system had to be completely seismically rated. But we're also being asked in New York now and other areas to also have some seismic capability. And if you look at the picture, different buildings have different ratings based upon, you know, the severity of earthquake potential in that area, the height of the building, the type of building. So there's all these different things that have to be taken into account. So how did we develop this? We had been installing up to 500-pound pieces of glass on walls with mounting systems that you wouldn't see physical parts of the mounting system come through the glass. So the glass would be just you'd have a small reveal and you'd have glass. And we were using different types of hanging systems, but there were ones that we developed. And we worked with third-party engineering services to do finite element analysis. We worked with Eckersley O'Callaghan to determine would this structurally be able to hold glass on the wall. And we also worked with installers such as Eureka Glass and Metal, they're out of Pennsylvania, on these systems. So we had new ways of mounting glass that we also had to test seismically for will these things meet the seismic forces necessary to keep them on the wall without damage. So this is one of our installations, which if anyone knows, this is in Philadelphia. It's, I guess I call it 13 stories high, but these are glass panels that range from 200 to 500 pounds. They're thick laminated panels. Any panel in any place at any time can be removed without having to move or touch another panel. So this was part of what we wanted to do, is make it easy to access a panel, remove it from a wall. We were then asked, in this situation when we were doing multiple panels, can it be seismically sound, seismically compliant to AMAA 501.6, which is the seismic test. So we took that and we went one step further. So Eckersley O'Callaghan ran a finite elements analysis on the system with the different sizes that we were planning to put in. They looked at drift in the X direction, so they looked at X, Y, and Z components singularly and additively to look at the stress on the system, stress on the lami, stress on the structural system that adhered it to the rear materials, which are extruded aluminum. And we kept on going back and forth with, if we do this, then what? They would test it and come back with, yes, it works, it doesn't work, maybe you want to try this. The resulting system became a plug-and-play system where we were able to use a standardized extrusion with preset cutouts that were able, like in some of the, what are they called, storefront systems where things kind of just fit and snap together. So we created a system that was almost a snap plug and play, went on the back of the glass, went on the wall, and kept things within plus or minus 0.005 inches to make sure everything fit tightly, because what you didn't want is to mount glass all over your wall and have them not line up. And we wanted to make sure that when it was mounted like that on a wall and the glass would move back and forth, that it was precisely aligned so it would slip past each other and not bump into each other in case of movement. So the test was done in July of last year in Fresno, 107 degrees out. And if anyone's been to the Intertech facility in Fresno, you see a line of buildings. There's facades there where people are testing all sorts of material. We're doing interior glass out in 107 degree, which is what, 42, 43 degrees Celsius. We're testing it for its seismic capability. So this 9/16 inch glass, which is 4 feet by 10 foot, so that whole thing is 8 feet by 20 feet in the air. 4 pieces when it's finished, each piece weighing about 300 pounds. was going to rack back and forth through a simulation where we start with tiny little bits of movement at the base, back and forth a half inch or so, and then it moves further and further back and forth at a relatively fast pace. And then it gets up to about 6 inches of movement, and it slows down, where the bottom is going 6 inches this way, and then 6 inches this way. The whole thing's moving. Each piece of glass had 15 screws just holding, that was what was holding it on the wall. And everything had to move back and forth. And the AMAA test is you have to go through this series of movements for it's about 6 minutes of time. And you can't have more than 1 inch, 1 square inch of material fall off the wall. That means glass, that means metal, that means anything that we mounted. So the whole system, a wall was built, sheetrock was put up, our wall mounting system was put on top of it, and then the glass was put on top of that. And if any glass broke off, any piece of that system broke off, and more than 1 square inch, that doesn't mean like a half square inch, a half square inch, and a half square inch, that wouldn't have passed. So as long as either nothing falls off or less than 1 square inch, the test keeps going. At 1 square inch, the test stops. This is footage that will bring us into what the test was. You'll see the movement. Can you start that? This is part of the installation. This is when it's doing about 12 total inches of movements, plus and minus 6 at the base. And the glass is sliding past each other, not running into each other. We heard that bang and we thought, what happened? And it was the end of the test. So we didn't know what to expect. And you go to these tests and you just don't know what, is it gonna work? Is it not gonna work? The analysis that was done assumed, not assumed, but the answers came back like, yes, it should work. But while you're going through the test, you're just, you're at your wit's end, nervous, what's going to happen? At that point, oh, can we go to the next slide? So at that point, the test was over, and that was it. It was like 6 minutes of moving the glass, and then that's the end of the test. So you take months of prep, and in 6 minutes, the test is over. At that point, we were rated as nothing fell off, everything stayed on the wall, so we became AMAA 501.6 compliant with the system. And for us, it was an accomplishment because we went from being what I would consider a decorative glass company to now, an architectural and decorative glass company that's providing mounting systems, because a lot of the architects were saying to us, we want one source responsibility for glass, for mounting, the mounting system, the process of doing it. So you're not saying, hey, oh, I'm only responsible for the glass, the glazer is responsible for the install, and if it doesn't work out, it's their fault, and they point at you that it's your fault. So we've been asked a lot to provide the whole system, and this allows us now to provide wall mounting systems for glass with our glass that are seismically rated. And that was accomplishment. We're happy about it. And I think that leads us to questions. Yes? Oh.
Excellent presentation, Jim. So we do a lot of work in testing and FE, and we always try to measure what we experience in a real test and compare it back to the FE model. Were you able to do that in the testing, like the difference in dimension between the plates of glass or things? Just curious if that data is available and what you experienced
Yeah, that's a great question, John. We didn't do that, but based upon having the video of everything that went on, we can probably analyze the video, find the distances things moved, supply that back to Eckersley, and have them look to see if that matched up with the model. So that's a good question, and we should follow up with.
Thank you for the presentation. It's very, very interesting. In terms of the aspect ratio of the panel that you tested, it appeared to be a double story, certainly taller than, say, a 3.5 meter story height. So is that specifically just for one project?
This was a test for a project that we had. We had to meet an L over something rating for the drift for that project. So every project was different or is different on what the drift is. So for a project that would be similar to this, that had the same level of drift, that had nearly the same height, it could possibly still apply to that. But there is the, like you're stating, if it becomes a different design, that would be tested again for that design.
Yeah, in New Zealand, we usually test to a particular value for a particular building too, based on seismic ULS and SLS drifts calculated by the structural team. Yeah. So are you familiar with many of the New Zealand codes? Or
I am not. We are familiar mostly with the U.S. ones. We're typically given this is the drift that needs to be met, and then we'll go with Eckersley and say, okay, here's the numbers that we get for that site. They'll apply it to their formulas, and we'll get feedback back and forth.
Yeah, after the Christchurch and recent Wellington events, there's been quite a lot of data in New Zealand in regard to the performance of different window systems.
Yes.
Generally, the structural silicone glazed systems perform very, very well. Obviously, they're lightweight as well, being glass compared to, say, concrete. But most window systems seem to perform very well, particularly unitized. Okay, thank you.
You're welcome.